Good evening, everyone, and welcome to ASFI Journal Club Session 3. It is truly a pleasure to see such a diverse group joining us today. I'm Dr. Najla Ataha, your session coordinator and moderator. I would like to warmly welcome our ASFI Journal Club participant, ASFI members, our guest audience, our respected Professor Bright Nuaro, our General Assembly leaders, and of course, our presenter for today. Thank you all for making the time to be here. Before we begin, I would like to take a moment to set the tone for today's session. Our journal club is multidisciplinary, and today's theme is Design Thinking in Practice, lesson from our own research journeys. This means that today is not about who understands the most equations or technical terminology. Instead, we are here to reflect on how real-world problems are identified, how researchers navigate complexity and constraints, what design and methodological decisions are made along the way, and how lessons from one discipline can inspire solution in another. Design thinking in this context is about how we think as researchers, how we frame problems, test ideas, and learn from failure and refine solutions. So please feel free to participate, whether your background is engineering, agriculture, health, policy, computational sciences, or the social and behavioral sciences. Your perspective is not only welcome, it is essential. Today's spotlight article focuses on mechanistic modeling of cassava peeling efficiency. At first glance, this may sound like a highly technical engineering topic. However, when viewed through a design thinking lens, it becomes much broader and more relatable. This study touches on agricultural mechanization, energy efficiency, reduction of crop loss, food processing scalability, and ultimately food security and sustainability. What makes this research particularly compelling is that it reflects design thinking in action, identifying a practical real-world problem, moving beyond trial and error, trial and error approaches, using modeling and stimulation to test ideas efficiently, and refining solutions before physical implementation. This is exactly the kind of research journey that benefit from cross-disciplinary insight and reflection. It is my pleasure to introduce Dr. Ide Chon. Dr. Ide Chon is an associate professor of mechanical engineering with extensive experience in development of engineering equipment, system modeling, optimization and simulation, and sustainable engineering solutions. He is currently a visiting scholar at Kabul University in Uganda, and is also affiliated with the Michael Obara University of Agriculture in Nigeria. His work focuses on using engineering and computational tools to improve agricultural processing, making it more efficient, scalable, and sustainable. Today, he will guide us through his study on mechanistic modeling and simulation of cassava peeling efficiency, sharing not only the results, but also the thinking, decision, and challenging that shaped the research journey. Please join me in warmly welcoming Dr. Ide Chon. Dr. Ide Chon, the floor is yours.
Thank you, the moderator. I hope I am heard.
Yes, yes.
Okay. Thank you, the moderator. Thank you, everyone. Thank you, ASFI family. I am Dr. Ede John Chijioke. Thank you. It's my pleasure to be here to share my research journey with my professional colleagues. It's a very rare privilege, and that cannot be taken for granted. Thank you. You are all welcome. And it is my prayer and wish that we're going to have a wonderful interaction. Thank you. Earlier, I am Dr. Ede John Chijioke. I'm Associate Professor of Mechanical Engineering, though I have already been introduced by the moderator. But just to throw a little light on that, my parent university is Michael Okpa University of Agriculture, Department of Mechanical Engineering. And I am also a visiting scholar to Kabale University, Uganda. I am on a national assignment providing technical aid to the university in Uganda. So I want to thank ASI family for this wonderful opportunity. My research experience is worth sharing, but I'll try to condense it within the limited time we have so that I will not take your time. Of course, I am aware that this is a multidisciplinary session, so I'm not going to bug you. Of course, I'm from engineering background, as I have earlier mentioned. So I'm not going to bug this honorable house with some technicalities on peculiarities from engineering background. I would rather prefer to share my experience in line with design thinking and research journey. I want to take a leave to thank this ASFI who has actually helped me to rediscover certain things about my research journey and then restore the confidence that my voice can as well be heard in research world. Thank you. Okay, straight to business of the day. This presentation, I'm going to look at it from this outline. We are going to look at it from this outline and we're getting started. Of course, we have already started. There's no better time to start than when you have started. And what are our motivations? Passion for local problem solving. A little background of my upbringing, which I would like to share with this family, is that right from my childhood, I actually come from Nigeria, West Africa. And in Nigeria, I come from the Southeast region. So I grew up among the agrarian community. So I have first-hand information and exposure to what was and what is and what continues to be the challenges we are facing down home. Of course, as a child, a growing child, I used to witness my parents go to farm. I discovered that most of the processing activities are done manually and traditionally. And right from then, this passion, burning passion in me, that I need to contribute my quota in solving some of these challenges. Like I will always say, we don't need a white man to come and tell us how to process things we have within our boundaries. That is part of the motivation right from childhood. The motivation I say, I will be a problem solver. I will join the clique of problem solving and DIY, do it yourself. So, and that has formed my research journey, even until this date. It is also part of the thing that propelled me to go into mechanical engineering. However, I have special interest in development of processing equipment. So we're going to look at this presentation from design thinking approach, I've said problem identification, framing, context and constraint, methodology and design choice, iteration and refinement during the study. Then key lessons cross the multidisciplinary. However, there are some technical terms that I just picked a few of them to just let us know so that we'll be acquainted with some terms. When I mention some terms, we'll be able to look at it. The work, one of this, our research output in agro equipment development is this paper, published article, which I'm sharing the spotlight now, mechanistic modeling. So mechanistic-based model, which is a physical law-based model that makes use of fundamental laws governing the behavior of systems or process to build their description and predict responses. These responses are performance of those systems. And then peeling efficiency is one of the key words that we have there, which is the ratio of completely peeled cassava tuber to the loaded mass expressed in percentage, and we have sphericity, which talks more about the degree of randomness of cassava tuber, how geometric mean diameter, thickness, mass of cassava peel, and these are intervening variables that we are going to meet as we go down. Okay, of course, this particular research was intended to answer the question of what, why, how, where, when, and what as a result, what were we able to get, which boils down to mechanistic modeling of peeling efficiency. And in the course of the study, we identified that performance parameters of most developed equipment, functions of certain input parameters, significant input parameters. And these parameters could be crop parameters or machine parameters. And then it can be operational crop parameters like shape, size, color, texture, and the rest of them, peculiar to that particular crop that the machine is going to handle. While the machine parameters has to do with certain machine characteristics like the length, diameter of the drums, and the rest of them. Operational parameters like speed are part of the intervening variables we looked at. Okay, going down to the main issue of the day. I am very much aware that this is a multidisciplinary settings, people from different backgrounds, but there is one important thing I need to mention to us, that hunger is a universal language, irrespective of your discipline. And that is why this area of study cut across all disciplines, because hunger is a universal language. And this research is coming to address food security. Okay. And cassava, just like in West, of course, cassava is mostly cultivated in West Africa. West Africa. What cassava is to West Africans It's like what Matoke green banana is to East Africa, where I currently work. And I don't think it will be wise enough for us to wait for a white man or the West to come and develop equipment that will need to process our God-given food crops. So the onus lies on us to solve our problem ourselves. I think that's what actually prompted. And this cassava that is mostly has a lot of applications as food products, livestock feed, raw materials. We have starch that is majorly used in textile industries, pharmaceutical. They're also used in pharmaceutical, and also used to produce biofuel, alternative source of energy. And then ethanol. All these things are the things that are gotten from cassava. And in the West African side, sub-region, over 90% of is one of the major crops that are found there, and over 90% of households consume these products directly or indirectly. Okay, but the challenge is that this cassava has to pass, this cassava product has to pass through certain processes for it to be ready for consumption or for raw materials. And if you look at the left, you see a flow chart diagram where we have cassava tubers, and then the processes, the likely processes we just adapted to help this presentation. Cassava tuber, peeling, washing is the first post-harvest activity that is done. Then depending on the end product or the derivative you want, and go for grating, chipping, soaking, fermentation. And as you move down there on the left, on my left, you see the product you can actually get. Starch for our textile industries, Gary. I was surprised that when I got to Uganda, they are not too conversant with Gary product. In fact, the cassava, they have cassava there, but they actually consume it directly the way we eat yam. So, and I think currently we are working on how to show them on further processing to get odd value added products. Okay. Cassava flour, fufu, which is general, and then tapioca. That reminds me, I remembered in my village those days when we were growing, there is this greater abacha. People from the Nigerian part, especially the southeastern part, knows that there is this delicacy, we call abacha tapioca generally, that there is this tool that was invented that they used. My mom those days used to grate the tubers after boiling. And those things were the things that motivated me that if people could come up with this and we with the exposure we have, we can do better. Okay, so this cassava processing has, if you look at most of these processing steps, where we have major issue is the peeling. Peeling has posed serious challenges, and it has actually affected its full mechanization and commercial. And what are the reasons? The challenges hindering peeling mechanization are irregularities in shape and sizes of cassava. Cassava comes in diverse shape. You cannot tell cassava tuber which shape it should come with. The only thing is that you are going to walk around it and know how to deal with it. Traditionally, before now, what is dominating is the manual peeling method, which has been adjudged to be almost the best method. Okay. So, and there are also variation in peel thickness and texture. These are the things that actually influence the final product. Of course, peels have to be removed because of there's some toxicity are also contained in the peels that are not good and safe for human consumption. So it has to be removed. It is a very major and one of the first post-harvest operation researchers have actually worked hard to come up with some peeling method, which starting from manual I have mentioned, and developing some tools which assist. And if we go down, you look at, these are some existing machines that people have actually tried to work on to solve this problem. Yes, but however, they still face some. These are preliminary solutions, but they are characterized by pre-operational treatments. Some of these machines can only work when you have performed some pre-operational treatment, like trimming, sorting, grading before peeling, so that the system can align properly with that. But there are challenges. How do we peel this cassava and without going through this proportional treatment and meet up with the huge demand for cassava products? That actually spurred us into our research in peeling. And the intervention led to development of the peeling machine, which you are seeing on the green down. This peeling machine works with on attrition principle, which I'm going to explain later. Okay, like I've said, these are the, if in and one at that time, if you look at this picture, if you are looking at this picture, one at that time tried to do some serious work in addressing the challenges of irregular shape cassava, which actually limits its peeling mechanization. He developed this spring-loaded peeling knife mechanism, but the challenge it had is that there are much flesh losses, which is not to be encouraged because it increases post-harvest losses because of processing. Okay, so this machine that we came up with is unique, very efficient. It works with a peeling ball. If you look at, this is the machine developed, and it is a Michael University of Agriculture, tested, confirmed, very efficient, and peeling. If you look at on top of this machine, you see balls. These are the peeling balls that work with the other peeling mechanism that are in the machine. If you look down, you see the peeling ball, you see perforated drums here. So the peeling balls aid. What is the job of this peeling ball? The peeling ball actually aids to assess those recessed areas in tubers, which you cannot control. They are natural occurring phenomena, so you cannot control it. So these peeling balls are actually loaded with the cassava. These peeling balls are made of gauze folded in balls. So in our preliminary experiment, we didn't just come up with this because one Professor Ezekwe in 1979 was the first person that proposed that if you have a enabling, he called it enabling ball, that it can help to assess those recess areas and peel them so that you have. So, and we actually took it up from there and noticed that it's not just having balls mixed with the cassavas in the peeling chamber, that you actually need to determine the shape of these balls and number of the balls with the weight of tubers that is loaded to guarantee efficient peeling. So this machine was actually developed and tested and optimized using response surface approach, and we discovered that it is actually working. And then we will still have problem of replicability, replicating, because most of the challenges we have down here in Africa is if we have problem of documentation and standardization of things. And I think it's one of the bases that led us to this. So as demand for efficient, faster, smarter, and more adaptive processing technology grows, the cassava processing industry should be advancing beyond the conventional method of manufacturing. Just manufacture, once it works, that's no problem. But if a demand is placed to get another type, you begin to do a lot of trials and error. That informed on why we need to standardize these things and build a model that should should be able to, of course, we know even in the conventional medicine now, gone are days when you go to hospital, you tell a doctor, I'm sick, I have this, I have that. The doctor, from the question he asks you, will begin to prescribe drug. And these days, in the medical profession, you need to go for lab tests so that they know exactly what is your problem with you. You can agree with me on that. So it is the same way we felt that there are things we need to know about this peeling technology and peeling mechanisms that should enforce, which we can document and test and make sure that if anybody replicates this, you will be able to have that. So the problem identification that prompted this research that I have shared earlier, we discovered that it is actually desired that any developed machine should operate with maximum efficiency, throughput, minimum flesh loss, and specific energy consumption possible. So any equipment with maximum efficiency at minimum specific energy consumption remains our standing target of present-day researchers and design engineers. Okay, so and then this machine, when you have it, it needs to be versatile. You need to peel cassava of all shapes and all age, maturity, which we have found out that these things are intervening variables in the development of the system. Okay. Going forward, of course, our goal is to develop a physical-based model, and then some of the specific goals is to identify and ascertain the level of significance of prop machine and operational parameters that can influence performance. The mathematical relationship from the mechanics of attrition peeling, to develop simulation model that will implement this mathematical model and to conduct experimental validation. Okay, so having said this, all we have done to get this machine and they are working. So here comes exploring the modeling prior to fabrication, so that if a customer has a specification, this model development should help us to answer the problem of, okay, that if you have, with this your full specification which we have presented, we are going to give you a machine working on the attrition principle, I've said, with certain level of efficiency based on these specifications. And that will be able to guide the processor. Okay. So this model development, like I've earlier said, fall into empirical and mechanistic modeling. We have tried empirical modeling earlier before now. We use that, and a work has been published on the empirical modeling using response surface methodology. Okay, but there are challenges this empirical model has, which we need to address. The challenge is that it is data-based. It actually characterizes a particular machine. When you develop a machine, the data you got from that machine is what you are going to use to develop that empirical model. And it is peculiar to that particular machine. So it cannot work for any other machine of higher or different capacity. Okay? So that was what led to what model can we use to develop a machine or develop a concept that whatever capacity of machine you need, it can always work. And that led us to this mechanistic modeling. Of course, mechanistic modeling has been adjudged to be one of the best mathematical modeling approach, which uses the fundamentals, the basic laws, and the relationships to develop that. So that we use to work on our efficiency, peeling efficiency, which is one of the performance parameters, key performance parameters. And these are the model concept framework. Dependent variable, independent variable. If you look at this graph, you discover that the dependent variable, which are the responses, the performance parameters, are actually peeling efficiency, specific energy consumption, flesh loss, but we concentrated more on the peeling efficiency. Okay? And then the independent variable are crop parameters, machine parameters, and operational parameters. Of course, these are the shortcomings, the strength and shortcomings of empirical modeling and that of the mechanistic modeling. When we looked at it, we discovered that mechanistic modeling will give us, it makes use of fundamental laws governing the behavior of systems and processes to build their description. No, not subject to flaw in data collection. So if there is any flaw in data collection for any machine, a mechanistic model is not susceptible to that. Anyway, okay. Going forward, this mechanistic modeling follows certain iterative steps, okay, which comes with system description, choice of symbols, sign convention for the process variables. Of course, this process variable, is not all the variables or the input parameters that are significant enough to affect our performance. So we actually did screening to know the ones that are significant and their level of significance. And that informed us to come up with the major significant input parameters that were used in the study. Okay, application of fundamental laws of geometry, mechanics, thermodynamics, and constitutive. Of course, I said I'm not going to bother this house with most of the technicalities. So these are the steps we actually took to arrive at this. Okay, these are we made certain assumptions to help simplify our challenges and solve our problem. And of course, those assumptions in the course of validation, we discovered that we were not far from reality and we are home safe and dry. Okay, some of these assumptions are cassava tubers are irregular in shape and predominantly conical. We assume it's conical. It has A, B, C as diameters. Of course, that is where we got the definition of geometric mean diameters, which help our machine to tailor towards that and minimize flesh loss. Then we also assume that the true density of cassava is uniform. That is, the density of the flesh and that of the peels are the same. Okay? Then the peeling balls are egg-shaped. Like I said, we have optimized the egg-shaped peeling balls to inform that. And then frictional crisis is the same within the drum. Mass of the drum is negligible. I'm not going to bug you with this, but the concept, let me just mention that since the principle of operation of the machine, the developed machine is on attrition, wearing away of the cassava peels. So we use the basic equation of wear volume developed by Ackard and subsequently run by that's the equation you're seeing there. It formed the basis of our, and then the relationship between peeling efficiency, which I'm not going to bug this house with, because that's the development. Then the concept we use, the mechanism and the force interactions. We modeled the system as a drum. You can see the drum, the plain drum, the circular part, and then as if it is climbing an inclined plane. The black spot you are seeing here is the mass, in consideration. So we have actually looked at this mass as mass of cassava and ball together, climbing on inclined plane, and that informed our mechanistic development, which I'm going to run through, and maybe that should be for people in this area who may want to know more about development. And finally, we came to this equation, which is the peeling efficiency equation, and discovered that peeling efficiency is a function of all these parameters, both machine, crop, and the rest of them. Okay, so that equation will actually did a manual computation giving the predictors as you have here, and we'll have a 5 experimental runs to be able to get efficiencies. If you look down here, you see efficiency. These are efficiency for each of the experimental runs. Okay, and these are actually meant to validate, to compute the model. Okay. However, Another challenge came up. If you look at that equation, you discover that the equation is actually bulky, complex. So there are computational rigors that are associated with that. We also consider that these computational rigors can be eliminated or reduced if we develop a software, a simulation software that can be computing this for any specification or any capacity as required. And that led us to simulation of the developed model. Okay. Down here, you see these are the building of the model and the simulations. They are interrelated. We broke them down into 3 basic parts. So the system, the software, which is user friendly, requires that you input what the input variables are for at any particular instance, and it adds it up for you and calculate and give you the peeling efficiency, which is this. The final peeling efficiency is determined, is computed at this interface. Okay, so when we finish this, the simulation, we'll try to validate this our model by collecting real world data. We went to the machine that is already built, is in Michael, so conducted experiment, like I've said, with using the same input variables and compared it with what the model simulation result gave us. And we discovered that the error is within the range of, as you can see from this table. So it was concluded that the model actually predicts well the peeling efficiency. Okay. Summary of the findings or key takeaways from the research. Peeling efficiency, that is performance parameters, is a function of crop, machine, and operational parameters. So the developed mechanism model predicts peeling efficiency with over 99% prediction accuracy from the validation test. And then the developed user-friendly computer interface simulation model implemented the model, eliminating computational rigors of manual computation, which becomes trial and error. Then the model helps to standardize and develop different capacities of cassava peeling system using attrition principle based on end user specification, thereby eliminating trials and error techniques. Conclusion. The modeling and simulation of peeling efficiency became the transformative tool for maximizing efficiency and throughput at minimum flesh loss and specific energy consumption possible. It is therefore concluded that from the study that performance of any design machine can be modeled to predict performance given ever-varying input parameters, which are crop, machine, and operational. So this ultimately enhances product quality, promotes sustainability across food value chain, and then digitization and response to product and capacity variability. So its socioeconomic benefits included improved rural income, job creation, empowerment, and smallholders and SMEs, fostering more inclusive, resilient food. So it is no more going to be, it is when a customer comes and say, I want a peeling machine that will give me so-so efficiency and so-so capacity and the rest of them. You go to your model and be able to advise the customer appropriately. Okay. So reducing post-harvest losses through technology directly contribute to food availability, nutrition improvement, and poverty alleviation, aligning with multiple SDG goals. SDG 2, 7, 8, and 12, as the case may be. Now we're actually, this research was a pointer to addressing certain concerns of those SDGs. Okay, stakeholders from government, private sector, research institute, farmer organization must forge partnership to enable technology transfer, capacity building, and market access. Sustainability principle embedded in this modeling and simulation is Our target is promoting efficiency, minimizing waste, and reducing environmental impact. By modeling and optimization, the peeling process and utilization of real-time monitoring system and technology minimizes resource input. It's no more going to be, you try this, if it doesn't work, the material is wasted, you try another one. You will be fabricating with precision, and it's going to do what it is expected to do because something informed that your particular design, which is the model. The enhanced computational efficiency, reduce post-harvest losses. These are our recommendations that based on the results and the findings, the research came up with the following recommendation that if other performance measures like specific energy consumption and useful flesh loss are adequately modeled, like efficiency, the throughput of the processing machine can further be enhanced significantly. The end user specification can be sought for, analyzed, and in simulation run on the program before embarking on actual machine development to ensure optimum material and resource utilization. So the development simulation software are user-friendly, that its commercialization will aid fabricators and processors as useful tool and guide in developing varying capacities. That these techniques should be extended to a continuous process and not limited to a batch process, because the machine in question for now is a batch process. And if you want to increase mass production, we should find a way of pushing this concept to accommodate continuous process. Final thoughts. The study has provided useful insights on detailed modeling and observation of mechanical systems prior to the machine actual fabrication based on end users' specifications. These are our towards the generation of rapid prototyping digital technology, which is the N10, that you don't need to, you should have a digital model of what you have. You can work on it and be able to use it to maintain and optimize the physical system. Okay, those in the engineering will understand better. These are the directions we are looking at and the research needs to make this worthwhile. Enhancement of technology flexibility and integration, developing low-cost, user-friendly interface, and decision support tools. Development of scalable but cost-effective digital twin solution adaptable to the needs of small processors. Interdisciplinary and multidisciplinary collaborations is also needed. Like I said earlier in the beginning, that hunger is a universal language. Whatever discipline you are in, you have your own quota to contribute for food security. However you see it is because when you are hungry, it doesn't ask you the discipline you are coming from. So you have a role to play. That is what the point we are making. Then policy and market incentive for zone adoption. Designing supporting policy framework, including subsidies, tax incentive, public-private partnership to help processors assess this concept. And yes, it is worthy to mention that this particular paper has actually added some invitations that you can come and present an updated work on them, like one we have on 11th International Conference of New Energy and Future Energy Systems coming up in Macau, China, from July 7th to 10th, which they have invited us to come and speak more because they say they saw it and they feel the concept is worth looking at. Thank you. I know I may have taken our time, but please, so many things are to be discussed here. But please forgive me for keeping you too long with the technical jargons. Thank you very much, and thank you for listening.
Thank you so much. Thank you very much, Dr. Chiji for that clear and responsive presentation. Fantastic. Before we open the floor for discussion, I would like to remind everyone that this discussion is designed for multidisciplinary audience and guided by our theme of design thinking in practice. You do not need to be an engineer to ask a meaningful question today. Discipline-based questions are also very welcome. We are especially interested in the research journey, the choices and trade-off made, the challenges encountered, and how these ideas and approaches might travel across disciplines. Please feel free to engage from your own disciplinary perspective. With that in mind, let us get the discussion started. Dr. Chiji, okay.
Yes.
To kick things off, could you briefly share what first motivated you to focus on cassava peeling efficiency as a research problem, and how you framed it at the start of your research journey?
Okay. What actually motivated me is that, like I said, can you hear me?
Yeah, clear.
Yeah. Yeah. But I have noticed that cassava has a huge potential that you cannot control. And but the processing, there's a bottleneck in the processing line. And this processing is peeling. And this peeling, what dominated before now is manual peeling. And this manual peeling cannot meet the huge demand for this cassava product. And this peeling is a must-do operation before you can process cassava into any other product. The challenge they have is that cassava, like I said, cannot come in diverse shapes. You cannot tell it the shape it will come in. The problem, the challenge you have is how do I navigate and assess the whatever shape it comes in? How can a system solve these problems without operational pre-operational treatments recommended by earlier researchers that you need to trim, sort, grade, so that the system, like one at the time, 2006, worked on developing a knife edge spring-loaded peeling mechanism, but it ends up eating up the flesh, and that leads to heavy loss. So, having noticed that this peeling is a challenge, we are motivated on how do we solve this problem and get this problem and get a large scale peeling operation that is not relying heavily on this traditional method, given those constraints of crop parameters. So these were actually our motivations, and that led us to look at these peeling efficiencies in relation to parameters, input parameters that can influence it. So we study these input parameters, and then how do we navigate around it and make it and overcome it for it to favor the peeling, for it to improve the peeling efficiency, which is actually our target. Thank you.
Thank you so much. Fantastic. Thank you so much. Please feel free if you want to ask our presenter any question. Dr. Kiji, okay.
Yes.
Thank you so much. I want to ask you, what gaps did you observe in existing approaches?
Yeah, to put it simply, the existing approaches recommended pre-operational treatments, which I've mentioned, that you need to cut the cassava to certain sizes, grade them anywhere you have recesses. Okay, You need to, so that it will align properly with the peeling mechanism they have developed. Okay. So, and that operational treatment is time consuming, and it doesn't encourage efficiency. Okay. Because what it means is that you have to do grading, sorting, and aligning so that it will align with their peeling technology. Okay. And that gap is what our intervention, development of this peeling technology, have come to address by use of both the peeling drum and then the peeling balls combined. So the peeling balls actually assess those recesses, okay, in the course of the motion, because we also model the motion in the peeling ball. Of course, to go further on that, there are some certain terms, sticking speed, like I mentioned earlier, but I said I was not going to bother this house with some technical jargon. We actually discover that there is a certain speed with which our machine will be running, which is cassava attrition peeling machine. Is peeling by attrition, wearing away the peels. That there are certain speed the machine will be running at, and the centrifugal force will keep the material, both the cassava and the balls, at the surface of the drum, and they rotate together. Okay? At that point, there's no pin. So, in the course of our design, we discover that there is a certain speed you will run the machine, and both the drum, the drum will, the cassava and the balls will stick to the drum, and they will move it together. In other words, there will be no peeling, because it is that relative motion between the cassava and the surface, embossed surface of the peeling drum and the peeling balls that actually activates peeling. So if you walk beyond that speed, centrifugal effect comes in and there will be no peeling. And we were able to address it and recommend that this machine should not be run beyond certain speed. Of course, that's why I said operational parameters was also considered, which speed is the major operational parameter that can influence peeling efficiency. Thank you.
Thank you so much. Thank you so much. What lessons can early career researcher learn from this process?
Okay, very simple. What it means, like I earlier said, is that a researcher with this approach that we have presented, it means that before you embark on fabrication and development of any machine, that this research has actually provided you that you need to do the simulation work based on the customer specification instead of going to do trial and error. Don't forget, I said earlier that most of the challenges we have is that people will try something and may not take their time to find out why that thing works the way it works, and what actually influences the way it worked. So this research has actually presented to us that you can develop a mathematical model using mechanistic approach and simulate how a system should actually work before going to the actual. The idea, the benefit of this is that it is going to reduce this problem of material wastages, okay, and optimization of material utilization, okay. Resources, you save resources, because before now the conventional thing is that you try this, if it doesn't work, okay, let's try another one. So it eliminates this issue of trial and error. You will be certain, just like I said at the beginning, that in medicine now, in the field of medicine, especially in the West, most doctors cannot treat what they don't know. Okay? But before now, if you go to hospital, you tell the doctor, I'm sick, I'm having headache. The doctor will be based on assumptions and similar incidents will begin to diagnose what is likely going to be your problems. But with advent of this laboratory test, the doctor will know, okay, from the test, this is exactly what is wrong with you. And you'll be able to provide the right solution to your problem, not trial and error. I don't know if that has spoken to that.
Thank you so much. Thank you so much. It is clear, yeah. Thank you so much, Dr. Kijik, okay? And welcome, Dr. Iman. We have Dr. Iman and Flora and Abir. They have question. Dr. Iman,
Good
the
evening,
floor is
everyone.
yours.
Yes, and good evening, everyone. I am Iman Sobh. I am the ASFI Director of Science and Communication, and I am also a physician. But I think the topic you presented today is very interesting to everyone, as that changing what's happening in actual life, and also making sorry, making some applicable advancement on existing models or existing industry is an ambitious for changing the science and also societal situations in Africa. My questions to you is this model applicable to anything that's built before using in industry, not cassava specifically, can be applied to any agricultural product that have to be built before using? The second question is, what are your lessons from this journey you can give to all of us as scientists and those working in the scientific fields, how to take the ideas from observing, from seeing the gaps in the society, and they change it into an innovative idea or a solution for a problem. Do you have any motivations, any recommendations, anything to make us move forward? A lot of us have many ideas, but they keep it in brain and not transfer it into a project or research or even a project or entrepreneurship idea. Thank you.
Okay, thank you for the question. Starting from the last question, I think the advice I will give to our all of us as scientists that most of the solutions we are looking out for are also always embedded in the system. You cannot drive a car from outside. And I have come to realize that nature has a way of preferring solutions to certain things. I'm just thinking generally now that most solutions to a problem lies within the boundaries of that problem. That it is now your ability to identify what affects what and what influences what within that system. That the solution to that challenge does not lie far from certain properties of that system. Okay, so that's what part of what this our research journey made me understand. Just like I have earlier mentioned that you want to peel cassava, you need to understand cassava as a food product. What are the characteristics of this cassava? What are the properties it has? Those properties, physical features, mechanical features, or whatever, is contained as part of the input variables that will help you to generate a solution. Because you cannot solve a problem you don't know. Okay, so I think for we scientists, this has offered us an opportunity to look inwards for whatever discipline that the solution set for that challenge lies around that challenge. You need to identify what affects what and how it works. Okay, that's what I have to say about that generally. Then your first question, what was that? Say, trying to recall. Your first question, what was that? Your first question, please. Can you recap it? Let me.
This model applicable to any agriculture product
Thank
that
you,
can be
thank you. Immediately you asked that question, it reminded me of in East Africa, just like I mentioned, that what cassava is to West Africa is what matoke, green banana, is to East Africa. When I got to East Africa, I realized that even though they are the second largest producer of green banana behind India, the literatures are there. And till now, they have not developed efficient system for mass production. What is dominating there is majorly manual processing. You need to dehanding, they use knife to dehand, peeling, they use peeling. And currently, with this concept we have with my team in Kabale University, we are trying to see how to adapt this concept to peeling of matoke. Of course, you know, the materials are not the same, but the concept, the matoke there, which is the green banana, they call it matoke. That's the local name in East Africa. And it's a major staple food they consume there. Okay? That it needs to be peeled before it is used for any other product, either boiling and the rest of them. And this matoke has some physical characteristics. In fact, I use some of my students to characterize this matoke across varieties. See how some of these features vary across varieties. Because it is those variation and those physical, mechanical, and other engineering properties of these materials that will inform you of the solution set. So it may what I'm trying to say is that any product that shares similar characteristics with cassava, okay, this our model, this our solution can be adapted to it. What changes are those physical features which are part of input parameters that we are accounted for in the model. Okay, and currently that informed us. I'm working with some students to see how we can develop a solution. I was even surprised that they have to invite people from the president has there's presidential initiative on banana whatever in Busheni. They have to invite people from, I think, Germany to come and develop the machine for peeling. The challenge they have there is that you don't tell banana finger the size it will come from. It comes from so the shortcoming the system has is that it has a fixed peeling profile. So anything that is below that size cannot be peeled by that system. Anything that is above that size, a lot of flesh will be removed. So it's not a universal solution. So this particular model and which we are projecting is such that if that crop shares similar characteristics or something that is close to what we have and is to be peeled by the same principle, which is attrition principle we have emphasized on, that this model can be adapted to it. That is why we said universal, there's need for universal application, especially if cassava, which comes in diverse shape, or what I'm trying to say is that apart from cassava, this principle can be applied in potato peeling, yam, and any other crop, tuberous crop that share with that. I don't know if that actually answered yours. Thank you.
Thank you. Thank you.
Thank you so much. Flora, go ahead.
Thank you. Thank you for the opportunity. Thank you, Prof. John Edie, for the wonderful presentation. I'm excited about your work, which is providing real solutions to challenges we are facing in Africa. My name is Flora Namu from Kenya. My question to you is your innovation already commercialized or it's still a prototype? And have you patented it? And if you have patented, what were the challenges in the process of patenting? Thank you.
Okay, thank you. We are in the process of patenting it. We are in the process of patenting the machine, and hopefully, in no distant time, the patent will be out. And then the commercialization comes after that.
Thank you so much. Thank you. Dr. Abir?
Yes, thank you. Good evening, everyone. So my question is, I think you answer part of it as the first question from Dr. Imanso. It's about the use of this machine. I'm pharmaceutical scientist, so I need to ask you from perspective of pharmaceutical. So I think this machine is for modeling. This is cassava is for modeling only, not um, as model material. So we can use this for another material or natural polymer like gum, acacia gum, or guar gum, or anything for produce starch and also I think fibers. And I think my question is that is this machine used only for production of starch and separate the fibers, or we can use it for another thing? Not about agriculture, no, for pharmaceutical use. I see in your one of your slides you say that you can use this machine for pharmaceutics. So I want to say how we for what I think this machine is used as attrition. So is this for production of starch only? And also my question is about this machine is used for research or we can use it for industry. Can use this machine also. Thank you. Thank you very much for your presentation.
Okay, thank you. Actually, this research has succeeded in giving us a machine that can be used in industry to solve our problem, because eventually, at the end, the machine has solved our problem of overcoming those challenges of crop, varying crop characteristics that limits the mechanization of this particular operation, peeling operation. So it is what is developed has been tried and it is there and it is working. So just like the last participant asked, I said we are in the process of patenting, after which commercialization can come in. So it is actually out there to solve the problem.
So we use it for cassava for production of starch.
No.
Okay.
Because the issue, if you look at this flow chart by my left, you discover that for starch production, you see that you have to grate and the water. When you do water, you allow it to settle, the suspension to settle, and you get your starch. Okay? If you look at it. So we are at this point of operation that before any of these other products are realized, that peeling has to take place. And that is why it is occupying this immediately after harvest. It is just to be the first post-harvest operation that precedes any other operation, cassava peeling. So it is one of the operations, not the operation for processing starch. If you want to process starch, you have to go through these processes to get your starch. Okay. Well, if you are, for those of us in West Africa, Gary, you see, you have to go through this process and then get garification and you get your Gary, cassava flour. So these are the processes you have to follow to get. But this our machine is working at this level. Okay.
Thank you.
Thank you.
Thank you so much, Dr. Kiji for this insightful reflections and answer the question. And thank you for your time and for your great presentation. Thank you all for your thoughtful questions and reflections. Today's discussion clearly shows how design thinking strengthens research when we look beyond our own disciplines. We have seen how one study can speak to engineering design, agricultural efficiency, sustainability, and broader development and policy goals. This is exactly what the ASFI Journal Club aims to achieve, learning not just from results, but from how research journey unfold. Thank you so much, our presenter, our participant. Thank you so much, Professor Nuaro. Thank you so much, Dr. Iman Subh, for your continued support. And I really grateful to our presenter for his time, and I know that we took from your time. Thank you for all this. Before we close, I would like to acknowledge that Dr. Domusani, President of the General Assembly, is unable to join us today. We thank him for his continued support and look forward to having him with us in the next meeting. Thank you so much to all of you, and thank you for your time. Thank you for your support. Thank you so much, and have a good evening.
Thank you, Dr. Najah, for a wonderful event, and good evening for everyone, and good night.
Thank you, all of you, for your coming today, and good night.